Welcome back, vehicle dynamics enthusiasts. So last week we talked about the car as an overconstrained system and how the vertical loads at the contact patch of one wheel are dependent on all the vertical loads that the other three wheels are seeing as a function of spring stiffness and damping rates. Today we're going to use some more slow-mo footage to explore visually some more vehicle dynamics concepts, and we're also going to focus on some of the differences between GT cars and prototypes. So we've got three main areas we're going to focus on today. First one is ride. The second one is the vehicle's response in different chassis modes. And the third one is contact patch load variation and spring stiffness. So let's get straight into the video and look at this side by side of an LMDh car and a GT. The first thing you'll see here is the difference in roll angle. The LMDh car's got a much lower roll angle than the GT car. And also, as we open the video again, you can see that the ride response is very different. The natural frequency of the LMDh car is higher and the wheel travel is less relative to the GT car. Pause. So what do I mean when I say the ride response and the natural frequency are very different? The natural frequency is essentially a way to describe the rate at which a sprung mass oscillates in response to an input. So as I watch the car going over the bump, the body rises up and then there's some kind of oscillation as the body settles to its steady state value. The quicker this is, the higher the natural frequency is. So when I'm watching the prototype cars, I'm seeing them bounce at a higher rate than I'm seeing the GT cars bounce. And this tells us a lot about how the car is set up and why it's set up, as we'll explore in the rest of the video. The stiffer setups you see on prototype cars is essentially in efforts to control ride height. As we continue to watch more of this kind of footage, we can really see that the damping rate is a lot lower than the prototype car. The prototype cars, with the addition of their third spring, have a much different response in roll, heave and pitch. And that is because they have very different aerodynamic requirements, where the GT cars have much lower underbody aerodynamics and therefore a much lower aerodynamic sensitivity and require less control of the aerodynamic platform relative to the track surface. Because of the much higher spring stiffnesses, the higher damping rates, there's going to be a lot more variation in the vertical loads between the contact patch and the track surface. Okay, so how can I see that? The variation in the load which the contact patch is seeing is very strongly linked to the natural frequency. So let's take two vehicles of the same weight. One with a high natural frequency, one with a lower natural frequency. The higher natural frequency, the higher spring rate, is going to give a higher variation in contact patch pressure as it goes around the track and travels over bumps than the car with the lower natural frequency. So I can see that with the prototype cars, every time it goes over the bumps with the higher natural frequency, all these body accelerations are causing sharp spikes and rises and falls in the contact patch pressure. Whereas I can see the GT cars with the lower natural frequency have a much more consistent load, and usually that results in a higher average grip through the corner, and so all else being equal, it will generate more grip. With the additional compliance they have, the GT cars generally have more mechanical grip, and the prototype cars will do much better in the high speed corners where the extra aerodynamic loads will do a lot for the cornering speeds. That's another video using some great visual information to learn and teach about some of the engineering concepts that are happening to our favourite race cars around the lap. The next one's coming soon.